Hello Matrix and welcome to Wazimatrix. My name is Luni and today we're focusing on your final exam prep for physical sciences. All you need to do to send your questions and comments through to us is search for Wazimatrix on all social media platforms as well as our WhatsApp line. All of the details are on the screen. We've got a great assessment for you guys, so please check that out and download the 2Enable app for free on your app store. We also have a cool competition going on for you, so do stay tuned to get all of those details later on in the show. I'm not alone. I've got my favorite sign language interpreter, Nicolene, as well as our awesome teacher, Temba. Thank you so much, guys, and over to you.
Thank you, Luni. A warm welcome to you, Grade 12s. As part of our last push, there's probably 1,000+ things, for us to actually go through. But because of time constraints, we will focus on certain aspects that we genuinely, feel that you need to polish up. So we're not going to look at, a lot of things, but our focus today is purely on the paper one, which is the physics component of physical sciences. So without any waste of time, let's look at the final exam prep. Okay, right. We're going to use some of the problems that come from, the past papers. There will be certain points for discussion, but pay careful attention as well to, some of the tips in terms of the problem-solving strategies. What are some of the basics that you need to do as far as, approaching different problems. So we'll use only a couple of examples for the purpose of our exam prep. Right, here we've got the first question that reads as follows. An object of mass 1.8 kilograms slides down a rough curved track. Now what I'm going to do is I'll highlight the word rough. So this is basically some of the legal things that you need to bear in mind, that there will be those key terms within the context of the problem that you need to pay careful attention to, because they've got far-reaching implications as far as what could be potentially the catch, which is something that's unique for every question. So the word rough, exactly what does it suggest? There's a lot of implication to it. Remember, it says the surface on which the object is moving actually is rough. It means there is a frictional force that is exerted by the surface on this object as it slides down. But the direction of this force is also very important. It's always opposite to that of the motion. Right, and then this passes point A, which is 1.5 meters above the ground at a speed of 0.5 meters per second. So this 0.95 meters per second, let's think of it in terms of the initial velocity, okay? Right, we already are, breaking it down, collecting the data that would be of importance to us as we go along, right? And then it says the object reaches point B, that's the bottom of the track, at a speed of 4 meters per second. So we will think of this in terms of the final velocity. But remember, as the object moves, there is a constant frictional force that effectively acts on that object, right? Now, we are considering the motion of the object between point A and point B. So, in other words, let's think of position A as the initial position, which is why we're saying it's V initial, how fast it moves as it passes point A. And then we also ask ourselves, how fast is the same object moving when it passes point B? So our motion is confined between point A and point B. Right, now let's look at the scenario. Is this is the accompanying diagram for which explains to us what is happening. So our initial position in this case is position A. How high above the ground is position A? Is 1.5 meters, all right? So that's the vertical distance above the ground of the object when it is at position A. And then it reaches point B. But as it moves past point B, it is still in motion. However, you can immediately tell that as this object moves from A to B, it is actually moving faster and faster, right? Okay? Now, moving along, the first question. Now, if you think of, the basics in the physics paper, be it the chemistry, almost all these long questions, they definitely start with a definition. And remember, The definitions are those, the terminology that we use. It is the tool of the trade. That's the language. So for us to understand that, remember, we must refer to the examination guidelines for the definitions. Keywords must be used in the correct context. And beyond that, the definitions are typically all or nothing. So if the question says, for argument's sake, in this case, it says, define the term conservative force. Now, the 2 marks is all or nothing. So the keywords, or in terms of what a conservative force is, must be there, and it must make scientific sense. So what is a conservative force? It is a force, okay, very important. It is a force, okay, for which the work done, okay, for which the work done in moving the object, okay, in moving the object between 2 points, okay, right, okay, between 2 points, okay, it could be, in this case, A and B, okay, is actually independent of the path taken, okay, of the path, okay, right. What is very important in this definition is the fact that, remember, what does work on an object is essentially a force. So a force is exerted by something on an object. So we always talk about forces in terms of on, by, but in the context of work, what does work on an object is actually a force. Now, if a force is conservative, remember, the work done by that force is actually independent of the path that is taken between moving that object between any 2 points in space. So that's all or nothing. It's that or zero, okay? And then name. So the action verb in this case, name, you just identify the term. No explanation whatsoever. I think even the 1 mark suggests that you just say whatever it is without any explanation. It says name the conservative force that acts on the object. So the conservative force that acts on this object, we know of a conservative force, which is the weight acting on the object, okay? Alternatively, we would say the force of gravity, right? Okay, or force of gravity. Okay, now there's a lot of, misconceptions as far as force of gravity versus gravity. So gravity is a phenomenon with respect to the universal gravitation. Remember, any 2 objects in the universe, they tend to exert a force on each other. That force is directly proportional to the product of the masses between their centers, as well as, it's directly proportional to the product of the masses and inversely proportional to the square of the distance between their centers. So the main emphasis is between the centers. So gravity is the phenomenon as explained by the universal gravitation. But when we talk about a force of gravity, so say for argument's sake, I'm talking about the weight of this object, okay? We can alternatively refer to that force as the force of gravity or the weight. Or what actually we are saying is that by how much or by what force does the center of the earth pull this object towards its center? That's the weight. So that's a conservative force that acts on an object, right? And then moving along, it's still on the same scenario. Okay, now the question is mechanical energy conserved, right? As the object slides from point A to point B. It's a yes or no, but there's a follow-up to that. You have to justify your choice. So in this case, there's a keyword that we underlined. We said the surface is rough, and it suggested that there is a frictional force that acts on that object. As a result of that, once there's a frictional force acting on an object in a system, then that system is essentially not a closed system. So for that reason, mechanical energy cannot be conserved. So in terms of energy principles, as we know them from grade 10, you'd remember that in grade 10 we would have spoken about, the principle of conservation of mechanical energy, which says it should be a closed system for the total mechanical energy to actually remain constant. So as long as there is frictional force, then we know that the total mechanical energy will not be conserved, okay? Because the reason is that there is a frictional force, okay? A frictional force, not just any friction, kinetic frictional force, okay? because the object is in motion. Remember to distinguish it from the static friction. So there is a frictional force acting on object, okay? Right. So the frictional force is the one that causes the mechanical energy not to be conserved, right? Moving along, still very on the same scenario. Now the question on calculations. So routine calculations are a very common feature of most of the structured questions in section B of, be it, you know, the chemistry or the physics. So in the physics part, I think you need to also recall very well that if a question is 3 marks and the action verb suggests that you need to carry out some sort of a computation or a calculation, remember the 3 marks suggest that you identify the correct formula as it is given in the data sheet. So you copy it correctly. No mistake about that. And then secondly, do the correct substitution. However, before you carry out any substitution, ensure that the necessary conversions in terms of the SI units are also done correctly. And then the final answer is not just the magnitude. Sometimes it could incorporate direction if it's a vector, but also what is of importance is the correct SI unit. So formula, substitution, answer for a routine calculation. That's straightforward, okay? So calculate the gravitational potential energy of the object when it was at point A, right? So this is the quantity that we are calculating. So the formula will be EP, right, is equals to mgh, right? So we need to ask ourselves, okay, what is the mass of the object? Okay, I'll just go back. The mass is 1,8. There is the mass of the object is given. How high above the ground is the object when it is at point A? It's actually 1.5 meters, okay? Right, so having said that, we can then say, okay, the gravitational potential energy, not just potential energy, gravitational, okay, it's 1,8, and then the constant 9,8 multiplied by 1.5, right? And then already the 2 steps that we have carried out, they carry a mark each. So the final mark actually has to do with the correct value of the magnitude of gravitational potential energy together with the correct SI unit, all right? So now in terms of the final value, we definitely have to use the calculator to determine the magnitude of gravitational potential energy, right? In this case, we're gonna have 1,8 multiplied by the constant acceleration due to gravity, which is given again on the table of physical constants, multiplied by the perpendicular height above the ground, which is 1,5. So this gives us a value of 26,46 joules, okay? So we got 26,46 joules, but remember, gravitational potential energy is a scalar, so we only concerned with the magnitude of that, right? And then moving along, okay, still on the very same scenario, now using energy principles, okay? Now, one of the most important, you know, mind maps in terms of understanding, you know, because the question may say use energy principles. In other words, it suggests that you may not use equations of motion. So there are essentially 3 energy principles. We've mentioned one, the principle of conservation of mechanical energy as we know it from grade 10, that talks about the total mechanical energy remaining constant as long as it's a closed system. And then we also know that we've got the work energy theorem, okay, that talks about the work done, you know, by a net force on an object being equal to, you know, the change in kinetic energy. And again, the last one, we also talk about the work done by a non-conservative force. Now remember, we've got conservative versus non-conservative forces. So if there is a non-conservative force that acts on the object, it simply means the mechanical energy will not remain constant, it will change. So the change in this mechanical energy equals the work done by that non-conservative force, right? So the energy principle that is of importance to us here is work done by the non-conservative force equals to the change in mechanical energy. So to break down the EMEC, we have got the change in kinetic energy plus the change in gravitational potential energy. So this is more or less of, yes, it is a routine calculation, but because there are many aspects to it in terms of, first of all, determining the change in kinetic energy and the sum in terms of the change in gravitational potential energy. And the work done by non-conservative force is actually the same as work done by the kinetic frictional force, okay? So that is very important. So the main thing that we just wanted, aspect that we wanted to capture here is the energy principle that is concerned, okay? Just to wrap it up on this segment, there is a question that says the surface BC is frictionless. So BC is actually the object moving from B and moving to C. Now we are told that this surface is frictionless, okay? Now, if the surface is frictionless, it means that there is no frictional force acting on the object. As a result of that, we know that this object will move at a constant speed. And according to the Newton's first law, we know that when an object moves at a constant speed, actually the net force acting on it is equals to 0. So the value of net work, which is done, the net work is done by the net force. So if there's a 0 net force, then it means the work done on the object, the work net done on the object is also equals to 0 joules, right? So that's the main idea as far as that. Luni, because of time constraints, over to you.
Thank you, Themba. Matrix, let's take a quick break and we'll see you straight after this. Welcome back from the break, Matrix. If you've just joined us, we are still doing your final exam prep to help you with the upcoming exam. If you're constantly running out of data, then this next competition is just for you. Waza Matrix is bringing you the hashtag WazoWinner competition, where 2 lucky matriculants stand a chance to win 2 gigs of data. So all you need to do is head on over to our Facebook page and all of the details will be there. Thank you so much, Themba, and over to you.
Right, in the second segment, we're going to look at a different question as a point for our discussion. Electrostatics is part of the work that we would have covered in grade 11, which is also examinable in our metric exam paper 1. And also, not only grade 11, because remember, in grade 10, we would have discussed some concepts around the principle of conservation of charge, the principle of quantization of charge. Those are some of the legal things that you need to revisit and make sure that you're on point on that. Right, in the next question 2, again, also adapted from DBE November 2019, a small sphere Y carrying an unknown charge, okay? So there's a sphere there, it's suspended at the end of a light inextensible string. Now, the light inextensible string suggests that the mass of the string is not going to be taken into account. So we're going to ignore it in terms of light. And then also, if it's inextensible, it purely suggests that it does not stretch. So if it is connected to some object of some sort, then there's a constant tension force that is on that string acting on the object, right? Which is attached to a fixed point, right? Another sphere X carrying a charge of positive 6 times 10 exponent negative 6 coulombs on an insulated stand, right? The moment we're saying insulated, so those are some of the key words in terms of the principle of conservation of charge. Remember what it says. It says, in a closed system, the net charge remains constant. So insulation is a way of saying that the charge, the total charge that is in that system will remain the same, okay? And then it is brought close to sphere Y, okay? Right, so here is the scenario. I think the accompanying sketch, I think further, illustrates what is happening in this case. Now, sphere Y experiences an electrostatic force, right? So sphere Y experiences an electrostatic force and comes to rest. It comes to rest, okay, 0.2 meters away from sphere X with the string at an angle of 10 degrees to the vertical. So that's the vertical, which is represented by the broken line, okay? So this sphere Y is at rest because of some electrostatic force that acts on it, because maybe of the force that is exerted by the string on sphere Y, okay? So those are some of the little things, right? What is the nature of the charge on sphere Y? okay? Choose from positive or negative, okay? If we go back to that sketch, sphere X has got a positive charge, okay? Now, if sphere Y is to remain at rest due to an electrostatic force that's exerted by sphere X on Y, it says that the nature of charge of sphere Y must be the same as that of sphere X, right? So when you talk about nature of charge, it says in this case either positive or negative. So we know how point charges interact in space. So because there is a repulsive force that we can deduce exists between those two spheres, we can immediately say sphere Y is also positively charged, right? And then now for sphere Y to be at rest, it means then we can immediately deduce that there is a force by sphere X on Y, okay? So this is force by X on Y. Yet at the same time, because in terms of the Coulomb's law, we also appreciate the fact that this is the force by sphere Y on X. So these two forces are actually equal in magnitude but opposite in direction. Okay, that needs to come to mind. Then this repulsive force that exists between these two spheres is a result of these two spheres having the same nature of charge. In other words, they are both positive, right? Let's move along. Then it says calculate the magnitude of the charge on sphere Y, okay? If the magnitude of the electrostatic force acting on it is 3,05 newtons. So the electrostatic force is given in terms of magnitude. And we already said there's a force by Y on X, and then there's a force by X on Y in terms of the Coulomb's law. So the question is actually 3 marks. And we have already indicated in the previous segment that if a routine calculation has got 3 marks, it's identifying the correct formula from the data sheet, doing the necessary conversions before substituting, okay? And then carrying out the calculations and then including the correct SI unit, okay? So in this case, this is essentially about the Coulomb's law. So which says the electrostatic force is equals to K, which is the constant, okay? Qx, Qy, that's their product, divided by r squared, which is the distance between them, okay? So what do we have here? We've got 3,05 as the force that is given, and then the value of K is given in the table of physical constants. Make sure you copy it correctly. 9 times 10, exponent 9. We are given the charge of X, which is positive 6, times 10, exponent negative 6, multiplied by charge Qy, which is the unknown in this case. And we are told that it's actually, if you can quickly check, the distance is 0,2. This is the distance between the spheres. You know, in terms of the distance between the centers, it's not important in this case because the charge actually accumulates on the surface of the sphere, okay? Right, so this is 0,2. Do not forget to square that. Okay, what follows subsequent to this is actually evaluating the value of Qy. So the learners, it's also important that you know, we are not looking for the magnitude of the electrostatic force in this case. So it's advisable that you do the substitution in the equation as it is given. Do not attempt to isolate Qy in the, like, for argument's sake in this case, because in the process, chances are if you make a mistake, then you know it kind of affects everything else, and you may be penalized for that. So from here, you are able to isolate Qy and actually determine the magnitude of the the charge of Y. So if we can quickly go to the calculator, very quickly. What we have here, if we are going to isolate Qy, it means we're going to multiply the electrostatic force by the square of the distance between those two charges, Qy and Qx, which gives us what? 3, okay, because it's going to be a ratio, so it's going to be 3,05, okay? That's the electrostatic force multiplied by 0,2 squared, okay? Then we're going to divide that by, you know, the K and the magnitude of the charge on Qx. So K is 9 times 10 exponent 9, okay, multiplied by the charge of x, which is 6 times 10 exponent negative 6. Okay, this gives us the final answer, which is actually the charge of qy. So in this case, we're getting 2,26 times 10 exponent negative 6. Okay, so it's 2,26, all right? Okay, so this is 2,26 times 10 exponent negative 6 coulombs. So what we essentially did there, we also gave the answer correct to 2 decimal places, which is basically what is expected, unless or otherwise it has been specified as part of the question, all right? Right, and then moving along, then draw a labeled free body diagram, okay? I'm going to underline that. Okay, the free body diagram is a critical component of the physics. In most of the questions that involve forces, we are either asked to draw a vector diagram, we are either asked to draw a free body diagram, or we are required to draw a force diagram. We need to ensure that by this time, going into the exam, we know the differences between the three. Okay. Yes, they tell the same story. However, we need to be specific because the examiner specifically requested that demanded of you to write, to draw a free body diagram. So this diagram is actually free of the body. So in the place of the body, we'll have a dot to represent that diagram. And then remember, it's the tail and then the arrowhead which shows the direction. Okay. And in most cases, these questions on the free body diagram are not exactly, scale drawings. So the magnitude or the length of arrows is not something that we'll particularly pay attention to in this case. So we want to draw a free body diagram on sphere Y. So what is important, this is about sphere Y, right? So here's the scenario, okay? So there is the dot that represents sphere Y, okay? And again, let's also pay attention to the number of marks that are awarded for that question. If there are 3 marks, it means then we also include 3 forces, okay? Right. So the first one, we've already talked because we say there's an electrostatic force by X on Y. So that electrostatic force actually pushes Y away from X in that direction. So that's F electrostatic, okay? That's 1 mark, okay? And remember, the tail must touch the dot, otherwise you'll be penalized for that. Also, do not forget to include the direction of the force, okay? And then the other one, that X on Y, because Y has got a certain mass, then there is obviously the weight or the force of gravity acting on sphere Y. So we already have 2 forces. The third one, because these are forces at equilibrium, why are we saying at equilibrium? We're told that sphere Y comes to rest. So if sphere Y comes to rest, we can immediately deduce that the net force acting on sphere Y is equals to 0 newtons. So these are forces at equilibrium. So this is the tension force that is exerted by the string on sphere Y. So these are the 3 forces that we are, we're required to identify. And also, furthermore, because we are saying that the sphere Y comes to rest and the net force is 0, the implication of that is we are able to also draw a triangle of forces to show that the resultant force or the net force acting on sphere Y is equals to 0. So that is something that we can do. That's the tension force, okay? It's in that direction. We did not change anything, okay? That's the weight acting on sphere Y, which is our Fg. And then the weight and this electrostatic force are actually perpendicular to each other. So that's the triangle of forces that we were speaking about. And then we know that this is actually 10 degrees. Okay, so the tension, the string is at 10 degrees. So this is our 10 degrees. And then meaning that by implication from your geometry, obviously these 2 must add up to 180, the interior angles of a triangle. Then this is obviously 80 degrees. Okay, so you can use then your trig ratios subsequent to this to actually determine whatever the question may demand of us. Okay, so we've drawn that. Okay, and then it says calculate the magnitude of the tension in the string. Okay, so this is our diagram. Okay, this is our diagram. If we can quickly go back to the sketch of the closed triangle forces. We know we want the tension, that's what we're looking for, all right? We know the electrostatic force is 3,05 newtons, okay? So we just need an angle and, you know, one of these three sides of this triangle. And then it says to us then from our trig ratios, we can use the sine rule, okay? So sine of 10 degrees is equals to, for argument's sake, the opposite, which is the electrostatic force divided by the tension, okay? Now, in this case, we can simply say, okay, because we've got the tension, we've got the electrostatic force. So sine of 10 degrees is equals to 3,05 over t, right? Then you can isolate t. Or you may use the cosine in terms of the 80 degrees. And then if you say cosine of 80 degrees, okay, is equals to F electrostatic, okay, divided by the tension. Still, we've got the F electrostatic, which is cosine of 80 degrees, okay? Cosine of 80 degrees is equals to 3,05 divided by t. It will definitely work out to, you know, the same thing. Right. Now, this is one of the, you know, multi-step type of a problem that you'd have maybe required to do, because it involved a number of, you know, concepts altogether, but there's also mathematical skills that are important. Now, two small charge spheres, A and B, on insulated stands with plus 2 times 10 exponent -5 and -4 respectively are placed at that distance. M is the midpoint of the sphere. Let's quickly look at the sketch, right? So M is a point. Now, what we know, questions of this sort, you know, not only may they assess something on, you know, the electrostatic force in terms of the Coulomb's law. Also, it has a lot to do with electric field at a point, okay? Right. Then it says define electric field at a point. The data sheet as an essential tool, E is equals to F over Q, okay? Then if it says in words, we can immediately say that this is the force experienced per unit positive charge. Okay, so that's the force, okay, experience, right, per unit positive charge. Okay, per unit positive charge. So the word positive, very important because it suggests something about the test charge. Okay, so this is what we call electric field at a point. So that's the term, not electric field. So we need to be very mindful of that as well. Okay, Luni, because of time constraints, can just take a short breather. Over to you.
Thank you, Themba. Matrix, we are going to take a quick break. Please don't forget to enter the competition, as well as send us any questions and comments that you may have to help you prep for the exams. We'll see you straight after this. Welcome back from the break, guys. I hope you're still enjoying the show. Thank you so much, Themba, and over to you.
Thank you, Luni. Before the break, we had already looked at the definition of electric field at a point, which is something very, very important because it has far-reaching implications as far as some of the problems that we may need to respond in as far as net electric field at a point. Speaking of which, the next question says, calculate the net electric field at point M. Okay, let's go back to our sketch. So when we talk about E net, okay, we are saying that electric field at a point, let's say due to QA, right? Electric field due to QA is actually K QA over R squared, right? So what does that exactly mean? Point M is a point that is in the field of both charge A and charge B, such that if we place a positive test charge, right, that's the unit positive charge at point M, it will experience a force due to QA and due to QB, okay? Now, the idea is, if that is to happen, at point M, we place a positive charge due to QA. QA is a positive charge. The test charge on its own is also a positive charge. So let's draw a free body diagram or a vector diagram showing the force acting on the positive test charge due to QA and QB. So due to QA, because QA is positive, the test charge will experience a force in that direction due to QA. So let's call that E due to QA, right? And then charge B is negative. The same unit positive charge will experience a force due to QB in the same direction because they are opposite. So the test charge will be attracted towards charge B. So let's call that E due to QB, right? So if we talk about E net, we are saying the net electric field at point M is equals to E due to QA plus E due to QB. So the plus in this case suggests that it's the resultant or it's the net. But however, we're going to take direction into account because electric field at a point is essentially a vector quantity. So E net due to those two becomes 9 times 10 exponent 9. The magnitude of QA is 2 times 10 exponent negative 5, right? Okay, right? Divided by how far is point M from charge A? It's actually, we're told that M is the midpoint. So M is, both charges are equidistant from M, okay? Well, in opposite direction. So in other words, this is 0.2, do not forget to square that, plus E due to QB, which is 9 times 10 exponent 9 multiplied by 4 times 10 exponent negative 5, right? Divided by 0.2 squared. You'd realize that for B, we did not include the negative because the negative will mess up our vector in terms of direction, okay? But we are using the vectors in terms of the direction. So the vector diagram allows us to determine the correct direction. And then we can quickly go to our calculator there and determine the magnitude of E net, okay? So in this case, we have 9 times 10 exponent 9, which is the constant, multiplied by 2 times 10 exponent negative 5, divided by 0.2. Do not forget to square that as well, okay? And then plus another fraction, okay? 9 times 10 exponent 9 multiplied by 4 times 10 negative exponent 5, okay? Should be negative 5 divided by 0.2, okay? We square that as well. So we've put that all in our calculator. So it gives us a value that's so huge. It's 135, 1, 2, 3, 4, 5, 6. It's 13,500,000, okay? Right, so now our final answer then becomes E net is equals to 1,35. I've just expressed that in scientific notation, times 10 exponent positive 7 Newton per Coulomb, right? So because it said the magnitude of net net electric field at point M, then we are only concerned with the magnitude only. All right, and then that was it. Okay, now the multiple choice is another critical aspect of the physics as well as the chemistry paper. But today, because we're focusing on the physics, the skill that goes into how we respond to multiple choice. Ideally, as a tip, it's advisable that you start with the long questions because long questions, they focus on a specific topic, within the concepts within that topics. Yet the multiple choice will touch on this and that. It's all over. So in terms of organizing your work, it could also serve to reduce the levels of anxiety, which is something that is perfectly natural if you are preparing for an exam. So the multiple choice is very important in terms of approach. Let's use this as an example. It says a ball falls from the edge of a table. Okay, ignore effects of air friction. I'm going to underline ignore effects of air friction because that statement it means a lot in terms of whether the system should be considered as a closed system or not. Okay, are there conservative forces or not? You know, so the possibilities are endless. So pay careful attention to that statement, which says which one of the physical quantities associated with the ball during free fall, during the fall remains constant. Okay, I'm somewhere else. During the fall of the ball. So this ball, it's falling, there is no friction, okay? Now, there are 4 possible options that are given. And matrix, you'd remember very well that question 1 in both papers is actually multiple choice. And these multiple choice are not exactly of, you know, of the same level of challenge or demand in terms of the thinking that we have to apply. So a 20 marks kind of a question deserves at least 20 minutes or to 30 minutes, you know, depending how you manage your time during the exam. But you also definitely need to allocate a decent amount of time to answering the multiple choice. Otherwise, a lot can go wrong, okay? Right, so looking at the very same question, then in terms of feedback, these are some of the options that, this is the distribution of the choices that we made, okay? You know, about 10% saying it's option A, and then you've got about 5% saying option B, and the majority is saying is C, okay? While another 15 or so % is saying it's option D. Now let's look at the questions, okay? So look, the most common one that was is C. Now, when you answer multiple choice, before you can eliminate the distractors, also maybe think about why you think that option is wrong, okay? Before you just look for the answer that looks very correct. In this case, they're saying kinetic energy remains constant, okay? Because remaining constant, that's another thing. Now, let's agree. If we are to draw a free body diagram of this object, okay, if we ignore air friction, what is happening to this object? Only the force of gravity acts on it. That's the weight, okay? Right? So if the force of gravity is the only force acting on this object, then there is a non-zero net force acting on this object as it moves downwards. So as a result of that, this object experiences a constant acceleration. Now, already we're linking this to Newton's second law. So if an object is accelerating, it means there's a non-zero rate of change of velocity. So if the velocity changes, kinetic energy cannot remain constant. For that reason, it's wrong, okay? The momentum, as long as velocity changes, the momentum will also change, okay? The gravitational potential energy has a lot to do with the height above the surface of the Earth. So if we say mgh, okay, I'm going to write that big H there. So as the object falls down, the height changes. Then under no circumstances will the gravitational potential energy remain constant. So the correct one is definitely Fg, which is, in this case, is the weight of the object, right? So these are some of the legal things that you need to pay attention to as far as the multiple choice, right? Okay, and then we have another one. The graph shows on the next slide, we'll go to that in a short while, and then it says the graph is not drawn to scale. It shows the relationship between gravitational force and a given mass. So the moment we see these two keywords, we are already thinking about the universal gravitation, which is Fg is equals to G, M1, okay, M2 for argument's sake, D squared, okay. So that's the concept that is involved in this question, okay. And then says the magnitude of the force on the mass at distance r and the center of the Earth is F. So let's go quickly to that. Here is the graph that shows the mathematical relationship between the distance between the centers, between the center of the Earth and that object, okay, right. And then what's the question? It says, okay, now the question is we must find x, okay? Now, because this is a question that is based on universal gravitation, we know that this gravitational force, according to, in this case, is to do with this mathematical relationship, which means the gravitational force of attraction between any two objects is inversely proportional to the square of the distance between their centers. So when the distance is r, the force is F, right? When the distance is doubled, which is 2r, the force is a quarter of the original one. And then when it is 6 times, we want to know what's going to happen to the value of force in terms of F, right? Okay. Now, here are some of the options, okay? The vast majority, once again, they say it's C, which is like 65% or so, okay? And then very few people thought it's option B, okay? And then we've got about 10 or so percent saying it's A, and then 15% saying it's D. Now, let's quickly go through it, right? So this is what we are saying here in this case, right? So F is equals to G M1 M2 over D squared, right? So if this is actually, okay, in this case, they actually used R as the distance. So I can write this in terms of G M1 M2, okay, R squared, which represents the distance. The distance is R, okay? So this is our F, okay? Now, the distance between the centers is 6 times the original one. How is that going to affect the force in terms of F? So we are saying it's still the same masses, we assume, okay? And then we've got what? 6R squared. We square the 6R. This reduces to G M1 M2 over 36 R squared, okay? Then it obviously reduces to G M1 M2 over 36 R squared. So this is as good as saying 1 over 36 F, okay? So that's how we arrived at the correct option. So it was a way of showing that we understand the concept behind the principle, you know, which is, in this case, is the universal gravitation law. So obviously the correct answer is D for that reason. So these are some of the legal things that you need to pay careful attention to in terms of conceptual understanding in as far as the multiple choice is concerned. Luni, because of time constraints, I think we can go do as much, given the time that we have. Over to you.
Thank you, Themba. Matrix, we're wishing you everything of the best for the exams. Please don't forget to use our resources to study and help you prepare. Congratulations to all of our competition winners who will be announced on Facebook after the show. Don't forget to check out our schedule on www.wasamatrix.co.za, and if you missed any of the shows, they are available on our YouTube channel. Thank you so much, guys, from me, Luni, Nicoline, and Themba. Goodbye.
Goodbye.
Wasamatrix 2021 Catch-Up is brought to you by the Department of Basic Education, NECT, ETDP-SETA, SABC, MultiChoice, and DBE TV on OpenView Channel 122 in partnership with